Algebraic method. Consider the reaction C4H10 plus O2, then CO2 plus H2O. This equation could be balanced by inspection, however, we will use it to illustrate another approach, the algebraic approach. To balance a reaction algebraically, we start by putting unknown coefficients in front of each molecular species in the equation. X C4H10 plus YO2, then Z CO2 plus WH2O. Then we write down the balance condition for each element in terms of unknowns. In this case, there are four unknowns: X, Y, and Z, and W. From carbon balance, we have the condition 4X equals Z. The hydrogen balance is 10X equals 2W. And the oxygen balance condition gives 2Y equals 2Z plus W. This constitutes a set of only three equations for the four unknowns. The fourth condition comes from recognizing that chemical equations specify the relative amounts of reactants and products. Thus, one of the coefficients is arbitrary and all the others can be expressed relative to it. Thus, we may take one of the coefficients to be 1 arbitrarily, which then leaves only three unknowns and three conditions to determine them. The choice of which coefficient to set to 1 is completely arbitrary and may be taken to be the one that is most convenient for solving the problem. In this case, the choice X equals 1 allows us to arrive at a solution almost immediately, for then it follows that Z equals 4 and W equals 5. From the oxygen balance condition, Y can be determined to be 2Y equals 8 plus 5 equals 13. So Y equals 13 divided by 2. Thus, the balance equation could be written as C4H10 plus 13 divided by 2O2, and then 4CO2 plus 5H2O. This is a perfectly fine way of writing the equation. However, customarily, it is preferable to express all the coefficients as integers, in accordance with the law of combining volumes and Avogadro's hypothesis. Thus, we can multiply through the equation by 2 on both sides. It can be treated as an algebraic equation in this way and obtain the final result: 2C4H10 plus 132, then 8CO2 plus 10H2O.